This is Mrs. O'Neill for AP Chemistry, Chapter 8, Section 2, Ionic Bonding. I'm going to go through most of this rather quickly because most of this is review until we get to the lattice energy. I'm going to spend a little bit of time there towards the end of the notes and end of the video. So you should have watched Bozeman Science, Mr. Anderson explaining ionic bonding, about covalent versus ionic, sharing versus transferring. He talked about sodium chloride and how they become very stable as ions when they reach that electron configuration. He talked again about the different ions, one being a cation, one being an anion. He gave you a little mnemonic. He gave you a flow chart. He brought in that Coulomb's law, of course, very, very important. He talked about how the larger charge of the ions means that there's a larger attraction, but the greater distance between those ions would have less force of attraction, which should make sense. He talked about how these ionic compounds are crystalline structures. He talked about their stability. He talked a little bit about lattice energy, and he compared the sodium chloride to sodium fluoride, sodium bromide, and sodium iodide. And again, he's showing you the different numbers. So just take again into consideration where those ions are in the periodic table. Why would sodium fluoride have more energy required to break them or make that bond? Well, it's because those ions are closer together, because fluoride is smaller than chloride. But then on the other hand, bromine would be less energy, bromide ions, because those are bigger ions. So again, their ions are farther apart, doesn't take as much energy, as well as with the sodium iodide. Then he said, well, here's a 2-to-2, there's a 1-to-1 ratio here. There's also a 1-to-1 ratio with barium oxide, but now instead of +1, -1, it's +2, -2. And how does that differ in energy? So back to your packet of notes. Hopefully you will remember to pause the video, copy down the information, and then play to hear my explanation. The objective in this section is to understand the ionic substances and their attractions between opposite charges. And this is the big one. Energies of forming ionic substances and describing that lattice energy. Not going to say much here except for this. An atom with low ionization energy. We want to remember that ionization energy means losing that electron. So metals have ionization energy because they tend to lose or give up those electrons. Electron affinity really refers to non-metals most of the time because they are the ones that have an affinity for electrons. They want those electrons, so they're going to gain those electrons. So ionization energy, think metals giving away electrons, and electron affinity, think non-metals gaining electrons. So here's an example of how the sodium and chlorine ions form. Sodium has a 1 valence electron because it's in group 1. Chlorine has 7 valence electrons because it's in group 17. This is a perfect match because sodium is going to transfer its 1 electron to chlorine, forming that +1 ion, sodium, and the -1 chloride ion. And they both have now the noble gas configuration, making it sodium chloride. If I were you, I'd pause the video, try to do this on a scrap piece of paper. How is the electrons transferred between calcium and fluoride? Yes, most of you would know that the answer is CaF2, but how does that come about? Well, calcium has 2 valence electrons because it's in group 2. Fluorine again has 7 valence electrons because it's in group 17. Calcium is going to transfer its 1 valence electron. So now this fluoride ion is happy, but calcium is not. It still has 1 to give away. So there needs to be another fluoride ion to be formed. So we have 1 calcium with a +2. 2 F's with a -1, and that's how we get the CaF2 or the calcium fluoride. So Coulomb's law, again, it's brought up that there's a magnitude of force and it's going to be dependent on those particles. So Coulomb also said that the energy between those ions is directly proportional to their charges and inversely proportional to the distance between them. So that should make sense. This is a formula that is given. You do not have to know it. You won't have to use it, but you again need to understand that the attraction is twofold. There's an attraction because of the charges, and there's an attraction because of their size. So what is ionic bond formation? Well, a loss of an electron is endothermic. That should make sense. Think of that energy diagram. As we go up the graph, we are separating the atom from the, or I should say the electron from the atom, and that's endothermic. And if we look at chlorine, it's going to be a release of energy, or coming down that graph is exothermic, because the chlorine atom is gaining that electron. So those are coming together, and of course that's going to be exothermic. So if you look at those two numbers, the sodium to the chlorine is endothermic, those ions coming together, positive 147 kilojoules per mole. And again, we're talking about these ions coming together to make a bond, not necessarily interacting with them and forming like a chemical reaction. Okay, if that makes sense, hopefully. Okay. So I'd read over this, go through the next few slides, and hopefully you understand for which pair is the electron transfer from an alkali metal group 1 to a halogen group 17 going to be exothermic. Well, easy way to do this, find the lowest positive number. That would be your ionization energy. So the lowest positive number, or the lowest number associated with an alkali metal, okay, or any metal for that matter, that's going to be the lowest. And let's think of the greatest negative number, or the greatest electron affinity, and in this case it's actually chlorine and not fluorine. So you take those two numbers, do the math. Well, I'm sorry, I went too fast. Do the math, and therefore none of those two would actually make an exothermic. So it's always going to be an endothermic when ions are coming together to form that compound. So what do ions do? They lose, they gain. Ionic compounds form these crystalline solids. They align themselves to maximize the attraction between those opposite charges, but also to minimize the repulsion between them. So just like oranges are stacked up nicely, or logs are stacked up nicely, they come together as close as they possibly can with not too many spaces in between, but they're maximizing their attraction and they're minimizing their repulsion. Now this is where lattice energy comes in. Ionic compounds can stabilize ions that would be unstable as gas. So we're actually going to think about ions in the gas form when we're talking about lattice energy. Size of the atoms, I'm going to go through this rather quickly as well. You should be able to understand this from the periodic table trends. So here's a nice visual. We have lithium +1 to carbon +4. As we go across, we see that the ions get smaller. Makes sense because you're losing more ions. Where in this case, the nitride ion is going to be the biggest because it's gained the most ions. So that should make sense. These are all ions and one atom of neon who all have the same electron configuration as neon. They are called isoelectric ions because the Al+3 has the same number of electrons as the nitride -3 ion. So all of these have the same number of electrons, and that's how they would fit nicely as far as their sizes. So what is this lattice energy? This is the important part of this section. It's the amount of energy required to completely separate 1 mole of a solid into its gas ions, something we're not used to. We're thinking of ions when we put salt into water, it becomes sodium +1 and chloride -1 ions as an aqueous. Now we have to think of those ions as gas forms, a little trickier than what we're used to. So this is what it is. Lattice energy is taking the solid, and how much energy is needed to take that Na+ and make it Na+ gas form. How much energy is needed to take that Cl- and make it Cl- gas form. Okay? So that's lattice energy. So this should also make sense. The endo versus exo. Think of that that graph again, that energy graph, when we take a solid and we're breaking things apart. So when we're here and we're going up the graph, that's endothermic. That NX solid has to absorb energy in order to break apart into ions. And then, of course, the other way would be exothermic, right? We're taking those ions, we're coming down that graph. Oops, we're coming down that graph. And making it exothermic because we're bringing things together. So separating things out, bringing things together. Endo, exo, endo, exo. So here's a good example of lattice energy. And just like everything else, it takes a series of steps. So we have lithium solid plus our fluorine gas to make this lithium fluoride solid. This is a reaction that you normally would see. This is a reaction that you've seen probably before, how to balance, whatever. The total delta H of this reaction is negative 594. It's an exothermic reaction when these two get together. The problem is lattice energy says that we have to talk about the atoms, or I should say ions, in their gas form, which that's not what we have here. So it goes through a series of steps. Lithium solid becomes lithium gas. Not an ion yet. Lithium becoming a lithium plus ion, and the electron. This is your ionization energy. Your lithium gas atom becoming the lithium ion and giving away that electron, ionization energy, also takes energy. The F2 diatomic molecule breaking up into F atoms as a gas, but then this is electron affinity. The fluorine gas atom is wants those electrons to form that F negative gas ion. So that's also going to take energy. Then, of course, the Ni plus gas plus the F negative gas yields LiF solid. This is what we really don't know. We don't know how much energy that takes, right? Because these gas ions, they're not easy to come by, okay? But now, remember, this is the opposite of lattice energy. Lattice energy is this breaking apart into ions, okay? But we're going to go with making the solid first. Using Hess's law, there's our X, that delta H5. So again, plugging and chugging. So remember, this was forming the compound, and we really want the lattice energy. So we want that LiF solid to break apart into the gas. So we're going to have the same amount of energy, but flipping that sign. Okay, so that's what lattice energy is. Taking that solid and breaking apart into gaseous forms. So here's all the steps together, okay, in that nice little energy diagram, right? All of the energies going up would be endothermic. All the energies going down would be exothermic. So if we look at this, lattice energy is really the LiF solid, the lithium fluoride, breaking into lithium plus and fluoride negative gas phase. That's our lattice energy that we were trying to find, but the other way around. So calculating, again, there's always an equation. You don't really need to know what or how to use it, but know that it exists. So what is the magnitude of lattice energy? How do we get that value? Well, it's going to depend on the charges. It's going to depend on the size of those ions, and it's going to depend on the arrangement of that solid. So it really follows the trend of ionic radius. So if you need to go back and review that again, go back and understand how do ions gain or lose, and how do ions, what's the trend as you go across in the metals and the non-metal area, and what's the trend as you go down again in the metals and non-metal area. So this is a really nice visual. The attraction, of course, is going to increase as the atoms or the ions are smaller, and the attraction is going to increase as we gain the numeric values, the +1, +2s, +3s. This is just a little extra. The bigger lattice energy actually pays for that extra ionization energy. And again, ionization energy is removing those electrons, but it also pays for the unfavorable electron affinity. So it kind of pays for the other way around. And I kind of say pays, it's that energy. It's that energy giving up or that energy coming back down. Okay, so that O-2 gas is very unstable, but it will actually form part of a crystal like that barium oxide that he showed you. So those reactions that occur between those gases, ions, and forming that compound or the lattice energy going the other way around exist, but those are kind of hard to come by. We just know that they have to happen in order for that solid to actually appear. Okay, give it some thought. Hopefully you got that answer. and I'll see you in class.